Okay, I think we can start. So these are the filter design techniques. Impulse invariance, bilinear transformation. Okay, ji? Impulse invariance is simple to understand because only you have to, you are only scaling the frequency axis. That's really all you are doing. Even if you keep t is equal to 1, then it is the same, and you just replicate it at every omega of s. They are same. If you keep t is equal to 1, then you just replicate it at every 2 pi, and they'll give you the transformation. So we have seen the problems with it and the mathematical relationship, and then we covered the Butterworth filter design method, where you can design Butterworth filter using this particular expression of frequency. And in this there are two design parameters, n, capital N, and omega c. So you need 2 points. So these are the pole locations. So we covered this, that how you select the poles, and this example. Primarily we did this example, which just gives you an idea that how the filters are designed in analog domain. And then the conversion is pretty simple, that all you have to do is this is the HC of S which you get, and then you make partial fraction expansion, and then take inverse Laplace transform, and then the digitize it, and then take the Z transform. But it's a direct relationship also for converting it to a pole to a pole here to a pole here. So we covered this example. Then we started learning about bilinear transformation. So let me just it's a quick review. If you have questions, please ask. The problem with impulse invariance method is that it is a linear transformation. A linear means that you are only scaling the frequency axis, linearly scaling the frequency axis. So whatever your frequency response is, this is your frequency response, you are creating a small omega which is equal to capital omega into t. It's not doing anything else. Okay, but once you have this omega, then at every 2 pi, wherever that 2 pi occurs, you have to make a copy of it. Okay, so that copying is basically causing all the problems. That if this translation, the entire spectrum is within minus pi to pi, you are fine. But if it is not, okay, then you are in trouble, because then at every this you will have a copy, and every this you will have a copy. So there will be not only one, there may be many copies which are causing aliasing. So this is a problem, that this technique is not good for, only good for band limited signals. So this, if those of you who know who have learned the engineering drawing, the projections, it is really something like this, where you have a frequency axis in capital omega. Okay, so at every omega you have this frequency response, something like this. Okay, so it is a plot which is done. Let me try to make it a little more. This is, let's say, is the plot. SC J omega magnitude. So a linear translation is this translation from capital omega to small omega, and this equation of this line is small omega is equal to capital, as you can plot x and y. If t is equal to 1, this is a line with 45 degrees angle. Right? Now here is the projection, which is small omega and h exponential j omega magnitude. Okay, so now what you need to do is, but here you take a value of omega, read this value, go on this line, okay, and drop this value down. So draw this line here. So draw this line here. The only issue with this is that at 2 pi, once you are at 2 pi, you don't draw these here. So whatever you do after 2 pi, you need to alias it back into this portion, okay? Because this line basically is doing this. At every 2 pi, whatever, if you have something greater than 2 pi, it will come back because of this linear line. So anything which is above 2 pi, or in fact 0 to pi, will alias. So this line will cause aliasing, anything which is going beyond this. So you need a translation which is something like this, which never goes above pi, so that once you make projections, all these projections are within pi, okay? So this is the motivation behind bilinear translation, and really the motivation is somehow this is your frequency axis, okay, this is your capital omega axis, and you want this capital omega axis, the entire axis, to be mapped to another axis which never goes beyond minus pi and pi. So this is the real motivation. Somehow every value here is mapped to not exactly here but somewhere else, and where that relationship which says small omega is equal to a function of perhaps tangent inverse small, something like this, okay? So that is the relationship, that you first read a value of omega, read this value, and find out where to plot this value here, this value of small omega. So how you do that? Convert this omega into small omega, plot this value here, done. Then you go to next point, then next point, then next point. So you keep doing this, okay? And it guarantees that once you are doing this, even the infinity will be something which is less than pi or approaching pi, right? So the entire curve, once you plot it here, will obviously change its shape, but will be fit into minus pi and pi. So this is bilinear translation, right? So the relationship which makes this happen is the bilinear translation relationship. Okay, so this is the relationship, which is small omega is equal to 2 tangent inverse capital omega t over 2. This is the relationship that put the capital value of capital omega here, okay, and you will find a small omega. So this is how you translate. Read a value, plot it at that particular value of small omega. So it will fit into minus pi to pi. And this is the curve. This is how the frequencies are related. That you take a value here, you go and find a value here. So as you can see that no matter where you go, once you read a value and try to find out the small omega, it will always be within minus pi and pi. So because everything is within minus pi and pi, once you make copies of it at every 2 pi minus, so there will be no aliasing guaranteed. Once there is no aliasing means that if your the analog filter is meeting specs, it is guaranteed that this will also meet specs. Aliasing will not cause what happened in the impulse invariance method, where due to aliasing your digital filter is no more meeting specs. This will not happen here, okay, guaranteed. This will not happen here. So this is, people have come up with this curve, which is small omega is equal to 2 tangent inverse capital omega t over 2. So this is the curve, or this is the non-linear warping of the frequency axis. But okay, this is fine, frequency response, but I am not interested in really in this. I am interested in converting an HC of S into h of z. I am interested in doing this. So though I say okay, it is now the frequency transform has been, or the frequency response has been translated from analog to continuous domain, but my interest is in getting to this transformation. Okay, and this transformation really, what is shown here is really this translation. Okay, it is this translation which says that replace every s by 2 by capital T 1 minus z inverse over 1 plus z inverse. It is this translation. So wherever you see an s, okay, let's take a general case. A general case is, you can always take t is equal to 2 so that you just get rid of this, but remember the 2 means while you are translating the specs and then while you are translating the design back. So in both cases it should be 2. So now the example is, simplest example, 1 minus a z inverse. Okay, assuming and we'll go from this s minus sk, or even we can say s plus sk, for example. This is a single pole system. Okay, and sk is, in this case, I think negative may be appropriate. Sk is the pole, it should be negative. Okay, sk is a pole, it should be negative, because once you put it equal to 0, s is equal to sk, and sk must have negative omega, the sigma. So this is hc of s. Now I'm saying that using this translation will translate this hc of s into h of z. So what is that h of z? Okay, so you replace s by 1 minus z inverse and divide by 1 plus z inverse. So you do that here. 1 minus z inverse over 1 plus z inverse minus s of k, right? And this is equal to 1 plus z inverse into 1 minus z inverse minus s of k and minus s of k z inverse, right? So this is 1 minus s of k, and this is minus 1 plus s of k z inverse. Am I right in doing this? Okay. So then I take 1 minus s of k as, and above is this. Then I take 1 over 1 minus s of k as common. So I'll be left with 1 minus 1 over s of k, 1 minus s of k, right, into the inverse. So this is what happens to every pole. Every pole there will generate a 0. Okay, and this. As I know sk is negative, so 1 minus negative will be something smaller, and 1 minus plus will be larger. So this will always be less than 1. So this is the translation. So a pole s of k will map into this pole, 1 plus s of k divided by 1 minus s of k, and whatever the scaling and other stuff, but the location of pole will map like this. So this is the translation. Okay, so you replace every s in the hc of s by this relationship. Okay, and then we can always prove that in fact this relationship is that this relationship has this. If you separate z from here, this is the relationship, and you can always prove that this is same as what was written earlier, that small omega is equal to whatever. So z, if you write z, and let's not worry about t and t. Okay, so what is z? Z is r exponential j omega, and 1 plus what is s sigma plus j omega, and 1 minus sigma plus j omega. So this is what in s is. Okay. And we know if you take magnitude of this and magnitude of this, that is what we did last time, just giving you all the possibilities, taking magnitude of this and magnitude of this. It will be, we have a slide showing this, so let me just run that slide here. So this is what Z is equal to 1 plus sigma naught plus j omega naught, 1 minus sigma naught minus j omega naught. If you take magnitude of this and magnitude of this, the magnitude of this is magnitude square, and magnitude of this square is the real square plus the imaginary square, real square plus the imaginary square. Now there are several things which you can infer from this relationship. What are those things? Those things are, what if sigma naught is 0? Sigma naught is 0 means if you are on j omega axis. If sigma naught is 0, you are left with 1 plus omega naught square, 1 plus omega naught square. So what do you get? So cancels out, you get 1. Okay, let me again repeat. I want to see where the j omega axis is mapped. So put omega naught, sigma naught 0. Sigma naught 0. It will be 1 plus omega naught, 1 plus omega naught, cancels out 1. It means this j omega axis is mapped on the unit circle. We know where the magnitude of z is 1. It is on the unit circle. So j omega axis is in fact mapped on the unit circle. Now try a value of omega naught which is less than 0. We know if this is less than 0, then this will always be smaller than the denominator, so it will always be, z magnitude will always be less than 1. So means that left hand side pole will be mapped inside the unit circle. Okay? And similarly the right hand side pole will be mapped outside the unit circle. Then is this relationship. And it is coming from that S is equal to, again let's not worry about this, 1 minus Z inverse and 1 plus Z inverse. It is this relationship. So if you convert, write S is sigma plus j omega is equal to 1 minus R inverse exponential minus j omega and 1 plus R inverse exponential minus j omega, right? I am just writing value of Z, which is R exponential j omega. What if sigma is equal to 0? We already know if sigma 0, R is equal to 1. So R is equal to 1, R is equal to 1. So you are left with this expression which says j omega is equal to 1 minus exponential minus j omega over 1 plus exponential minus j omega. Okay? And this we know by a simple trick is reduced to this expression. And this is from where we started, that this kind of a relationship between a small omega and capital omega will result into a transformation which guarantees you that if a frequency response meets specification in analog domain, it is guaranteed that it will meet specification in discrete domain, which is not the case for impulse invariance method. So you are okay with this, and it also guarantees that a stable system will map to a stable system. So both the conditions are met, so this is a good transformation to be used. And so again the transformation is very simple. Once you have an HC of S, just replace it by that, and we know that it will be, every pole will have a pole in the Z domain. Okay, so this we know that the mapping left hand side will be inside the unit circle, and we know that this is the linear, this is the impulse invariance method. Okay, and here it never touches pi, so it is something like this. So it goes till this omega. I think I drew it the other way, but it is really like this. So no matter what value of omega you take, it will never come and hit pi. Right? This is the projection method, but if you so this is again the same thing. So it is the frequency warping of the omega axis. This is what I drew earlier. here is omega, here is the SCJ omega, and this is capital omega, this is small omega, this is the transformation. So graphically you can apply any kind of transformation, and how you do that, you drop projections here and you take those projections down and draw the same thing. So that is a transformation which, using engineering drawing, in fact you can draw these things, right? So this is the bilinear transformation design procedure. Perform frequency pre-warp to obtain the corresponding analog filter specs. So first of all, you need to use the same relationship to translate frequencies from discrete domain to analog domain. So you can pick any t, so preferably pick capital T is equal to 2 or 1. 2 is better. Then you design a C of S using the technique which we have already discussed, and then transform a C of S to H of C. That is the, so here is the same example, okay, the same example, but now first you need to convert this frequency into capital omega. And how you do this? It is using this formula, 2 over capital T tangent 0.2 pi over T. So use your calculator, find out a value. So that is this, and similarly you need to do it with this frequency as well. Keep T anything which you want. Keep capital T here, it says capital T is equal to 1, so capital T is equal to 1, just take this, but remember you must use the same value of capital T once you are converting HC of S back to H of Z. So you do the same technique, you know these are the specifications, and remember that if you know only 2 points, so this is the first point you know, and this is the second point you know. And also remember, this frequency is no more 0.2 pi, it will be whatever you get from here. This is no more 0.3 pi, whatever you get from here. So there will be a change in frequency, non-linear change in frequency. Okay? And you know these 2 points, that first you go through this point, then you go through this point. Okay? If you are designing a Butterworth filter, it will be monotonically decreasing function of omega. So knowing this, you get n is equal to 5.3, you bring it to 6, find out a value of omega of C. So it is this. So knowing this, now you design a filter and then use the bilinear transformation to convert that to H of Z. So these are few examples, but so it obviously the bilinear transformation will cause phase distortion because it's going through the frequency warping, which is a non-linear mapping. So even if you have a linear phase, going through this whole thing, it will be a non-linear. Impossible to get a linear phase filter, okay, because of the non-linear mapping. So if I show you MATLAB, let's use MATLAB. Now we know a little more to experiment with the filter design toolbox of MATLAB. So in this toolbox, so though these techniques are important to learn, so only then you will be able to design an appropriate filter. But knowing this, the MATLAB toolbox is a very powerful tool. So you really need not to really experiment with the design yourself. Don't go try to design Butterworth filter and all that, because knowing all the trade-offs, go here, invoke this, whether you intend to map it on FPGA or on a DSP processor or just simple on a general purpose processor, just use MATLAB toolbox, design it and export it to a header file or a C file, or so the important is learning the tool. So knowing this, now I know I need to specify a sampling frequency, I need to specify the pass, F pass, and I need to specify the F stop. Okay, I need to specify in dBs, if I'm doing in dBs, A pass and A stop. It is 80 dB down and it is only 1 dB. Okay, so I need to specify delta 1 and delta 2. So this is delta 1 and this is delta 2 in dBs. If you want to specify them in magnitude, you can do that too from here. And then if you want to specify an order, you say, no, I only want a 10th order filter. You click this, specify order. If you want MATLAB to give you the best design, let MATLAB do it for you. You say minimum order. Okay. Then you specify what type of filter you want, an FIR or an IIR. Because we have covered an IIR, so you say an IIR filter. So this is an IIR. Even if you are mapping it on a fixed point processor, you can in fact use these as well. You can set the quantization parameter. You say, I want these coefficients to be in 8-bit, 16-bit, 22 bits, is up to you, because MATLAB designs in double precision format. So you can always come and say, I only want the filter to be in this format and only 8 bits. So you may spend some time learning about this, but here is the IER. So Butterworth, you say Butterworth, and then you say design filter. Okay, so Butterworth is a very smooth filter. The interesting is looking at the, so it says a 31st order filter for these specifications, but I know I really am expecting these to be on a curve, because remember in S domain they were on the half of the circle of radius omega c. So these are now on here, and they are 31. Remember the 0 which was between 1 plus z inverse. For every pole there is a 0 at 1 plus z inverse. So if you count, there are 31 of these here. So every pole has a 0 here, 1 plus z inverse. Okay, so 31 zeros here, and all this is the other poles. Okay, then you can take these if you want second order section, means second order sections, or you want them in B's and A's. So you can know this. Usually we prefer second order section. Okay, second order section means that this is your second order difference equation. Second order, there will be 30 of these second order, 15 of the second order, and 1 will be a single order, because total order is 31. So we prefer implementing a filter using the second order. But if you want, for reasons, B's and A's in a single order, single section, so you can go and say, no, I want convert to a single section. If you say single section, I'll give you first the numerator coefficients, then the denominator coefficients, 31 of these. So this is how you design a filter. Then you say, no, I don't want a Butterworth. So it does not give you option to use a bilinear or an impulse invariant. We could always use this bilinear. Right? So it does not give you option. It says bilinear. Now you can say Chebyshev type 1, and we know what will happen in Chebyshev type 1. Okay? So you say design, it definitely will give you the same design in fewer number of coefficients. It says now only 13. Okay, and we also know where will you see the ripples. So or type 2, or you can say type 2, or you can say so elliptic filter. So almost all these filters have the same type of design practices or design methodology, that you have that equation, you solve the equation for unknown parameters, and then design. But end of the day, this is 8, so only 8 of the coefficients, 8 of the poles are there. So this really brings us to the FIR filter design technique. So in FIR filter design technique, so design them in discrete domain. The good thing about FIR is that direct discrete time designs are possible, and usually in analog circuits you don't design FIR filters, you always design IR filters. Okay, so FIR filters are special to signal processing. So you design discrete time filter. One method is the windowing method, and the other one is minimizing or the optimizing a min-max criteria, and I'll explain these two techniques. Windowing method is very simple to understand. It's simple to understand as we know that this is an ideal filter, right? This is an ideal filter, omega c minus omega c and 1. In discrete domain, this is an ideal filter. and H, I can say ideal exponential j omega. Okay, this is an ideal filter. So you start here and you take the inverse Fourier transform. If you take that, you will get a sink. We know that, sine omega Cn over pi n. We did this in chapter 2. So sine omega Cn over pi n has this limitation that it goes from minus infinity to infinity, number one. Number two, you cannot put it in a difference equation form. Okay, so these are two major limitations, because you know it is a non-realizable filter. So from where we started, we said this is not possible, so not realizable, so you have to do something about it. Either you design other types of IR filter, which we have seen, which are realizable, because you get a closed form expression in HC of S. You can convert them in H of Z and then to difference equation. But this cannot be converted into difference equation. There is no S in it. Okay, so it cannot be put in a closed form in HC of S, which you convert, or it is stable as well and all that. So that really says you, if you really want to use it, the only way of using it is shift it to make it causal and cut it. Okay, so you say, okay, shift the sink, it is the sink, shift the sink and cut it. Start from 0 and center should be in the center, and this. So you say, okay, from 0 to m coefficients. Okay, but you have to make it causal. So you make it causal, and we have seen type 1, type 2, type 3, type 4 filters. Those all filters represents a delayed version of this. Remember the n minus 2 alpha. It could be n minus 4.5, it could be n minus an integer number. So two possibilities. Either you have, once you shift it, it is n minus integer or n minus integer 0.5. So both will result into a symmetric filter. This we covered. So let's go on. So just reminds me that I have a lecture on Monday at 3 o'clock on statics for engineers. It's very different than signal processing, but any one of you who want to come, it'll be I'll be focusing on making like presentations and PowerPoint presentations, and what really you have to take care of once you are designing, especially putting multimedia contents, but different, like it's not engineering, just statics. So it will be at 3 p.m. on Monday. Ji? Idhar hi kahin in case. So, sorry. So this is what you do. That you delay it and then truncate it. You say, okay, first delay it and truncate so that you get a symmetric filter, one of those 4 types. Okay, so you get this, and this is really equivalent to this. The truncation is equivalent to delaying it and then windowing it. Okay, you say, okay, you first delay it. So delay is by either an integer factor or integer plus 0.5 factor. So you have this. Okay, and then you say truncate 0 to m. Okay, and mathematically the truncation is equivalent to multiplying it with the window. Obviously it is that if truncation, I can think of truncation as multiplying a window which runs from 0 to m. Okay, once you multiply, 0 multiplied by something is 0 and 1 multiplied by something is same thing. So it says really the windowing is the truncation is windowing. And now I can study the effect of truncation. I say, okay, if it is windowing, it means that in time domain I multiply, in frequency domain I convolve. Right? And this is to learn that what happens if you window a sinc function. Okay, so multiplication in time is convolution in frequency domain. Okay, a convolution in frequency domain. So, and it is a periodic convolution. Why? Because you take Fourier transform of the window and Fourier transform of this, And then you have to make multiple copies at every 2 pi. So once you are flipping and dragging, so you need to take the copy along, and I'll show you a slide which depicts this. So this is the formula for convolution. Okay, so you need to know the Fourier transform of omega. I already know Fourier transform of the ideal HD of n. It is a square pulse in frequency domain. So but I need to know the frequency response of this. So frequency response of a rectangular window, we call this a rectangular window, all one. This window is a sinc. Okay, it's a sine. So frequency response of this is a sinc, sine omega m plus 1 over 2 divided by sine omega over 2, and this is for the shift because it's shifted, but our at this point focus is really to learn more about the sinc, the magnitude. So the magnitude, if you plot it as a nice MATLAB slide which shows this is in frequency domain ideal filter. Its inverse Fourier transform is an infinite, though you cannot create infinite signal in MATLAB, so it's just representing something which is infinite, a sinc. Okay, now you want to window it, so it's a shifted sinc. You want to window it from here to here, right? Okay, you say this is in time. So in time domain, if you are doing this, is frequency response inverse Fourier transform is a sinc. Okay, the magnitude response. So this multiplication will result into a truncated filter which is realizable, which is an FIR filter. But this requires a convolution of this with this, and this convolution will cause, once you, let's go to the next slide and we'll come back to this. There is a slide which, yeah, so this is what is happening in the convolution. Okay, remember it is periodic at every 2 pi. So what you see at 0, so you're going to see the same thing at 2 pi. So it's a periodic convolution. Okay, so once you are here, let's say not even inside, there is no complete overlap, so to say, but there will be these ripples which will be causing some overlap, right? So there will be these ripples which will be causing some, although your the Fourier transform of the window is not in the main rectangle. Okay, so you start seeing something here, which is shown here. So you start seeing something, though you are still away from this line. Okay. So this will cause the stop band ripples. So delta of 2. So it will cause few delta of 2's, there will be some ripples here due to these effects. And then you are just keep dragging it and you start entering into rectangular window. Okay. As you can see, it will take you some time. It will take you some time to get inside the window. Okay. So that will be your transition band. It will be the area will keep on increasing. In convolution, what you do, you multiply this signal with this signal and then compute the area. So as you are moving inside the rectangular window, the area will keep increasing. Okay, and you will be here once you are completely inside the window, because now you have complete overlap of the main lobe to the rectangle. But as you keep on moving, these ripples will be going up and down. Okay, so that's why you see ripples here. So it will not be a constant because you are moving, and so there will be a rippling effect. Right? Similarly, once you get out of this, it will take you some time to get out of this, and area will be continuously reducing. And then once you are out, still there will be a portion which will be causing this response. Okay? So now I have few questions. First question is, I know the transition is not good. Okay, the transition band is not good because ideally I want this transition. Okay, what is defining the width of this band?
The window.
इसमें क्या है? In this देखिए the width of the, इसकी width जो है that defines the transition, because fatter it is, it will be bigger. Okay, and जितना इसको आप keep sharpening it, so it will be small. Okay, so the width of the window will affect the transition band. So the question is, ideally what should I have? Small as possible. Maybe if I have a sink, I know if sink is ideal. Okay, just an impulse is ideal, because impulse will just once gets in here, but if you take inverse Fourier transform of an impulse, it will be a window. Anybody knows the impulse? It will be all one from minus infinity to infinity. It means it requires you a window which runs from minus. What does that mean? It is same sink. It is same sink. Okay, so means this is not possible. This is not realizable. So all you can do is that as you keep increasing, I'll shortly show you the relationship of the width of this main lobe. We call this main lobe to the size of the window. And it's very simple inverse relationship. As you keep increasing the window size, okay, it shrinks. And ideally, if you go from minus infinity to infinity, the window, it will become an impulse. Okay, so means now if you want better, sharper transition, you use a window which has more coefficients in it. Okay, so here is, to go back, so this is the case. For example, for n is equal to 11, you get this. Okay, and now you can see, even spending 11 coefficients, I am still not getting something very close to ideal. 11 coefficient means 11 multiplications and 40 additions. So this is, so you increase, this is 41, this is 161 coefficients here. Okay, and this is still you see a transition, but it's a good response. It's a low pass frequency response. Now this is the relationship. M is length of the, m plus 1 is length of the window. So it is 4 pi over m plus 1 is the width of the main lobe. Okay, as you keep increasing m, so 4 pi over m will shrink. Right? So means put more and more into your filter, you will get better and better transition. That's a simple relationship here. Then what people did, they started like considering other kinds of windows. Okay? This was the time people were coming with different windows, and these windows are known by their name. For example, people thought that just an abrupt truncation of the sink is not good. So it was consensus that if you just abruptly truncate, you should not do it, because that is perhaps causing the side lobes. So people, first of all, they said, why if you truncated using a triangular window, so smoothly truncate it to 0. Okay? They said instead of using a rectangular window, use a triangular window. Okay, from 0 to m. It's not a smooth, it's a smooth truncation. And this is the formula. If you put different value, this is just this function. Okay, from 0 to m, it is a triangular window. Bartlett came up with this window. He said, try this. And then Henning came up with it. He said, why this? Why not maybe something like this, where you make it more smooth, because here it is not smooth at this point. So you're going up and you're going down. It says, why not to use a function of a cosine? Okay, a cosine. I'll show you the window. Then the Hamming said, why not this? This perhaps gives you even better results. And then there are people just coming up with a lot of windows. A black man came with this window. So that, as you can see here, a slight modification in all these windows. Okay. So Hamming is, this is rectangular. This is rectangular window. This is Hamming window. This is Henning window. This is Blackman window and the Bartlett window. So this one is the Blackman window. So these are the functions, and even in MATLAB you can go select a window yourself. You say I want to select this window. So what is the trade-off? So know this, they are just playing with the Fourier transform of the window, because we know this Fourier transform is causing these ripples, the transition and the other ripples. Okay, they thought that what if you try, this is a rectangular window or a triangular window. So this is the Fourier transform of a triangular window, minus 40 dB. For a length 20, it goes down to approximately minus, but here it is at minus something. So, but on the other hand, if you use a Henning window, you can see as you move away in the stop band, it keeps going down and down, even it hits minus 80 dB. Okay? So these are the trade-offs. But so the same length of the window has this frequency response, which you can wall with that. Okay. Similarly, this is Hamming and the Blackman window. A nice slide is where you see all of them together. So we'll shortly see that. So this is a good comparison of a triangular window with a rectangular window, and you can see the trade-off. The same length. Length is 41. Okay. As you can see, the triangular window is shown here. Okay, this is triangular window. Rectangular window, and this what you see in blue color is the triangular window. So what is the difference? Main lobe is wider, so it gives you better stop band rejection. The triangular window gives you better stop band rejection. As you see, it is more down than the rectangular window side lobes. Okay, but the rectangular window give you best transition band. The transition is best, very sharp transition, but then very high ripples in the stop band. This is the trade-off. You say you get better performance in the stop band, but you compromise on the transition band. If you are more concerned with the rejection, okay, you use for the same length. So you can always increase length to get better performance by a triangular window as well. But for the same length, a triangular window is better than a rectangular window as far as the stop band rejection is concerned. Okay. Similarly, here is a comparison of a Henning window with a rectangular window. Again, as you see, it is the stop band rejection is better as compared to the rectangular window. So this is Hamming window. So this was Henning, and this is sorry, I'm going. So Hamming and Henning. Okay. So again, this is almost the same thing. Hamming. The Blackman is, as you can see again, it is getting flatter and better stop band rejection. So the Blackman window is this. So this is a comparison of a rectangular window. You see here is a rectangular window, this one, and then is the Hamming window and the Henning window. Okay, and maybe it's not come to the Kaiser. So triangular Hamming Henning window, which shows that how you compromise on this is perhaps a better representation. So you see here is the rectangular window giving you very sharp transition, but then high stop band, and the other window, which is in this case triangular, is giving you a better stop band, but you trade off the sharpness in the transition to that. So how you design, same thing. First you have a sink. Sink is multiplied by a window, so you get something like this. So once you multiply sink, as you can see here, that this part will be multiplied by smaller number, this part will be multiplied by bigger number, so this part will be reduced. Okay, so you have a smooth truncation if you are using one of these windows. But it is really very hard, and I've in fact experienced that if you just keep trying, it'll be very hard for you to just keep trying this window, that window, this window, to find out which one is the best. Okay, so interestingly, the Kaiser, so Mr. Kaiser came up with a magical formula. He says, let's not worry about which window, because you can have literally infinite many windows between a rectangular window. Okay, it's just matter of putting a curve. You can just come up as you can fit infinite many windows inside this. Okay, so Kaiser tried to come up with a method where you just give you a specification in terms of the sharpness you want in the transition and the stop band rejection, and then it'll come up with a window by itself. It says this is the best window for your specifications. For example, if you have more emphasis on the transition, it will always give you a rectangular window. Okay, so a rectangular window is also a Kaiser window. Hamming, Henning, all these windows are Kaiser windows. So Kaiser came up with this. It says let's try to put a modified Bessel function of second type. Let's not worry about what it is. It's just a curve. Okay, it says, so you can put this as a window. Okay, and in this function you require a beta, okay, and m and alpha and m. Alpha is simply m over 2 length, but what should be the length? M is a design parameter, obviously. So you're giving specs and you want the Kaiser to come up with the length and the window. Okay, so window is coming from this function, and I'm saying let's not worry about this function at this point. It's just a curve inside that. So but here you need to know beta and alpha. Alpha is simple, but you need to know beta. So beta is the design parameter. So first of all, let's say, how do you compute the length? The length is computed using, these all are empirical formulas. What is an empirical formula? That the Kaiser tried several things and came up with these magical numbers. So just these are numbers, no rational, no math. It's an empirical number 2.285. Okay, it says put this and delta omega a minus a divided by 2.285 delta omega will give you an m. And what is a? A is the attenuation. Usually we keep delta 1 and delta 2 same. If they are not same, we take the minimum of the two here. Okay, so this is delta. You say delta minus 20 log base 10 of delta is equal to a. If it is 60 dB down, so a will be 60. So get an a, as you can see here. If Kaiser finds out that you are not interested in this rejection, you say a is less than 21, the beta value will be 0. Okay, so this beta values means that what type of window do you want. A beta 0 means a rectangular window. Okay, as beta value increases, you are moving away from a rectangular window. You are basically keep shrinking the window in time domain. Okay, and making it flatter and flatter in the frequency domain, and more rejection in the frequency domain. So m is computed from this formula. It's very simple to compute. As you can see from here, delta omega is the transition band. So it looks into the transition band, it looks into the rejection you want. Okay, so the rejection you want and the transition band will define length of your filter for the Kaiser window. Say, okay, you want this much rejection and this much suppression. I'll say this length will be enough. So this is m, and then use these empirical formulas. Again, no mathematical reasoning, it's empirical. And so the Kaiser came up with either the beta, I'll show you how beta affects the window shape. It says beta will be 0 if A is less than 21. If it is between 21 and 50, you use this formula. If it is greater than 50, you always use this formula. Okay, so these are the effect of betas. Let me go back here. Kaiser 2.0 is this. Okay, so the Kaiser 2.0, what you see here is Kaiser 2.0. Okay, a good transition, but so Kaiser 2.0 is this window, and rectangular window is Kaiser 0. Kaiser 0 is the rectangular window. Kaiser 2.0 is this window. Okay, and this is the response, frequency response. This is Kaiser, it will keep shrinking. Kaiser 5.0, this. And what you see in the frequency response? A flatter and more suppression. Okay, Kaiser 8.0 is this window. Okay, and 8.0 is this window, and this is the response. Even more flatter and more rejection. Okay. So the Kaiser, this is the Kaiser method. It's a very nice method because here you need not to worry about the actually figuring out the window. You just let Kaiser to decide. You just ask Kaiser, this is A, this is delta, and the Kaiser will come back to you. Will says, okay, for these, this is the best window. Okay, so the Kaiser method is a good method to use. जी स्टॉप बैंड की रिजेक्शन पे इफेक्ट कर रहा है. दिस इज द फ्रीक्वेंसी रिस्पॉन्स. ठीक है, फ्रीक्वेंसी रिस्पॉन्स इज दैट दिस इज हाउ द फ्रीक्वेंसी ऑफ योर the frequency content of your input signal will be shaped. ठीक है, means that you will get more and more rejection, means के they'll be completely eliminated the unwanted frequency contents. ठीक है ना, so this is the, it is, you are saying it is going down, means के unwanted frequencies as you move away. जी जी, oh yes, precisely. So this is the trade-off. Usually you say 3 dB down. So 3 dB down perhaps is not changing, but it is giving you, so perhaps this is 3 dB down. Okay, so design that 3 dB down is not changing, 0.707 is not changing, but otherwise once you go away it's giving you bad results. Okay, so this is again, I've already shown you this. So this is the Kaiser, and so Kaiser beta 0 is this, beta 3, beta 6, and again on the slide which shows you the comparative analysis and the comparison of the values, different values of beta. And this is an example where, so simple, like if you want 0.4 pi, 0.6 pi, omega pass, omega stop. Delta omega is 0.2 pi. A is minus 20 log base 10.001 is 60 dB. 60 dB, put this here, 52, this, 37. So M is equal to 37. And so and then you take these values, A is equal to 60, M value, and find out beta. And then if you know beta, then you draw this, the Kaiser window. In MATLAB, if you're doing MATLAB, you can figure out the Kaiser order by using a Kaiser order function. It'll give you the value of the n and the cutoff frequency and the beta. Then you take this value of beta and calling FIR1 function, give the number of points, give the cutoff frequency, and say you want to use Kaiser window. If you are using MATLAB function FIR1, you have the option to use Kaiser window, Hamming window, Henning window, Blackman window, all these windows by specifying that here. Okay, and here is n plus 1 and beta, and so you can just read through these functions, but preferably you need not to really go and do this, because MATLAB toolbox is a better way of designing a filter. So here is, if I go and just show you what is there. So now we come to FIR. Okay? Once you say FIR, you have all these methods. This is the window method. Okay? Once you say window method, it'll ask you which window. You can say Kaiser, you can say Bartlett, Henning, Blackman, so many. हर एक नाम की window है. So Henning, you know. So these are really the people who spend time in just coming up with the curve. So in case, so you specify a window. You say I want to Blackman. Okay, it's a Blackman window. It says so for Blackman, for these specifications, you are specifying the order. You say specify the order, because in window you have to specify the order. You say 10, you say no, it is not meeting specs, then it should be able to figure out. So this is the impulse response. Our interest is in the impulse response. Okay, so if you say window and you specify a window, then you need to also give the order. If you say Kaiser, there the Kaiser you need not to. You say Kaiser will give you the minimum order by using all those formulas. So though there are other, like for every window people have come up with empirical way of roughly figuring out the window length. So this is the Kaiser window. Okay, so the Kaiser, this is the filter which is designed using Kaiser window. Okay, not the window, the filter designed using the Kaiser window, and you can design any filter. So it's your choice, FIR versus IAR. Remember, FIR are always linear phase, zero phase group delay, the constant group delay. Okay, so this is the windowing method. Then there is another method, but that really is very complex to understand, because this method is McLaughlin's PhD thesis. So he came up with another method. He said, let's not worry about windows, let's try to do a Chebyshev. Remember, Chebyshev is the best filter. It gives you in minimum coefficient the best filter. Why? Because you are allowing ripples in the passband and in the stop band. So thinking on these lines, McLaughlin thought that let's not use a window, let's try to design a filter where we minimize the maximum error. Okay, it says allow the ripples to happen in the passband and in the stop band, and try to, instead of just minimizing the error, okay, try to minimize the maximum error. Okay, so minimizing the maximum error means that minimize this, because error is different. Minimizing the maximum error is different. You say if you minimize the maximum error, let it ripple as many times as it wants. Okay, so that is all error. So if something is like this, where your desired is this, so this is the error. Okay, so and you may have this band, for example, this is your delta of one band. So this, for example, is your band. As if you remember what the Butterworth does, it says let's do a smooth, though the error, the specs still says that delta 1 is equal to this much. Okay, if let's say this is 1, so the as much you are away from 1 is the error. Okay, so very minimum error, so to say. Minimum error. On the other hand, if I am just rippling in this, error may be much more than what I get if I just very closely keep moving with this line and then I drop. Okay, but for me, once I am designing filter, I don't care. All I care is that how much this band is, because that is defining my delta 1. Okay. So the Chebyshev approximation, again this is in 1972, it's a part of his PhD research, and he came up with a criteria which says that let's try to minimize the maximum error. It says this is the error, and it says this is the ideal response, and this is what you intend to design. And then this uses Riemann exchange algorithm to iteratively find the impulse response that minimizes the maximum approximation error over a set of closed intervals in the frequency domain, in the pass band and in the stop band. And those of you who are interested, there is in this chapter there are sections which talks about the Riemann exchange algorithm, that how it actually does that, how it iteratively tries to minimize the error. But the good thing about the method is that if you are designing a filter, okay, I in fact happened to start my PhD with Dr. McLaughlin. He's in Georgia Tech. So if you look at the Kaiser says, what is the order? 101. And if you say the equiripple, okay, equiripple is the Parkes-McLaughlin. So design. So the same filter can be done in 50 coefficients. You can just see the Kaiser used to be the best, because Kaiser says that, the best, just tell me deltas and A's and I'll give you the best window. And here in the half the amount of coefficients, almost half the size, you can design the same filter. So it's a very effective method. So this Riemann exchange algorithm is very, very effective, as you can see here. And though if you look at the frequency response, obviously there are ripples here and ripples in the pass band, ripples in the stop band. Okay, but it'll give you a very good filter if you use the Riemann exchange algorithm, which says. So this will lead to, as it says, equiripple approximations that are optimum in sense of smallest approximation error for a given transition width. So this is these are MATLAB functions. If you want to find a Butterworth order, this is the function. So in a Butterworth order is where it will give you the two design parameters, which is n and omega c. So Butterworth order will give you n and omega c, and then you use this to design a Butterworth filter. So for a Butterworth filter to design, you specify butter, n and omega c. Give these two, it will give you a Butterworth filter, B's and A's. Okay. So similarly, you can have other IAR filters in MATLAB, Butterworth with the Butterworth approximation, Chebyshev and all that. And I think this is the point where you should also start thinking about your project, which you need to do. An assignment दी हमने, so you need to give assignment and a quiz and whatever. A theory की assignment दें, MATLAB की assignment दें, और a quiz, because we'll be moving to the next section. Next class में quiz भी दे Monday को. Let them have a good weekend. So, okay, so this is similarly elliptic approximation in MATLAB, and so you can find all these functions. Elliptical filter, find the order, and then ask ellip, and it'll give you B's and A's. So in MATLAB, if you're not using the toolbox, you can always use these functions, and this is pretty much I intend to cover. So what I intend to do next is the statistical signal processing. So here, if I recap what we have done in this part of the course, it is all deterministic design. Deterministic is where you know this is your delta 1, okay? You know this is your delta 1. You know your omega p or small omega p, and you know your omega s. Okay? Knowing this, you say you have two options: either you design an FIR or you design an IIR. Okay? Knowing there is an IIR, you say there are again three methods. You either use the Butterworth, Chebyshev, or elliptic filter. Okay, it's your. But remember, it'll be using a bilinear transformation. And what a bilinear transformation does, it corrupts your phase. So there will be phase distortion. If you use this, there will be phase distortion. And the good thing is that a stable and causal filter in S domain will guarantee a stable and causal filter will meet your specification. If you're not too much worried about phase and group delay, you do that. So what we learned in the first part of the course is analysis. And analysis, we said Fourier, the frequency response is good because it tells you that how the frequencies of the input signal will be shaped. And then we said Z transform is good because it tells you something about stability. And all you have to know is all the poles are inside the unit circle. And how do you know that? So we'll find out. It's more challenging in the part where you really don't know specs. There are no specs. Okay? So you are on the fly, you have to design things. Okay? So there, whether you are doing IAR, you cannot go, you first find the specs in real time, then you go and you say either I want to do this or this or this. No. But you have to design a filter. In the second part of the course, dynamically you get a buffer of data. You have to design an IAR filter or an FIR filter with B's and A's in it. Okay? And then you have B's and A's, okay, this is fine, but then you have to check the stability. And how do you check the stability? You need to compute all the poles of the system. And then what you do, you have to check whether all the poles are inside the unit circle or not. So that will be done dynamically, okay, in real time. So you get data, you design filter, you check stability, okay, and then you implement. The next buffer, you again do the same thing. Okay? So we will be doing that. And then obviously you can do an FIR. An FIR, you know, the windowing method is one, and the minimizing the maximum error is the other one, which gives you an equiripple filter. And in windowing method, there are so many of these windows are there. Okay, the best perhaps is to use a Kaiser. It's a Kaiser, and Kaiser will give you the order of the filter as well. But the optimal one is equiripple. That you say, let's do the equiripple design. Equiripple design will give you the most economical filter. Similarly, FIR can also be designed adaptively. Almost all equalizers, they are FIR filters. Okay, though they need to be IAR, but they are FIR filters. Especially in equalizers, you don't want to waste time in actually figuring out the stability. Okay, so usually what FIR filters are, if you go in adaptive filters, you will learn about LMS, NLMS, you know, all these filters, all these techniques, least mean square error. So you design FIR filters. You say you have these coefficients. The coefficients are changing all the time. So in LMS, least mean square, you compute an error. You say you have usually you have a transmitter, and what you transmit goes through a channel, and then the channel you receive. Okay, from digital communication perspective, what you transmit is a signal, a bit. If you are transmitting a bit, okay, it is 1 bit every time you spend some time transmitting bit. How you transmit bit? Through this channel is number of ways. One is you use, for some time duration, you use a sine. Okay, you say I'll send a sine if it is 0 and a cosine if it is 1. Okay, so means you change the phase here. If it is 0, you send this. Okay, on the other hand, if it is 1, you send this. So there is a change of phase, right? So you detect this change of phase at the receiver. So where there a change of phase happens, it means it is 0 or a 1, and you only know till this time period. If it does not happen in this time period, it means you are sending the same bit, a 0 and a 0 and a 0 and a 0. Okay, so this going through, this is either you are sending 0 or a 1. But once you receive, it's let's say amplitude 1. So once you receive, it may not have an amplitude of 1. Okay, and the more interesting is the case where you are sending 2 bits. If you are sending 2 bits, there are, here it is 180 degree phase shift, then there will be either you don't phase shift or you shift it by 90 degrees, 180 degrees, 270 degrees. Okay, so there will be 4, either no change, 90 degrees, 180 degrees, 270 degrees. So then you need to be more precise in figuring out the phase change. But the interesting thing is that once it goes through the channel, okay, you don't receive what you send, because channel has a frequency response. The channel has a frequency response. Channel also has an impulse response. Okay, so channel usually has an impulse response which is not linear phase, which is not symmetric, which is just it is there. So you need to, before you send it through a receiver, we know if it is an H of Z, you need to design an HI of Z. The problem with HI of Z is that the HI of Z will always have poles, because all the zeros here will appear as poles, and we don't like that. Okay? So now the challenge is that you want to design an HI of Z which is an FIR, and you still want to cancel the effect of H of Z. So you want an HI of Z to be an FIR, and you want that you design it in a way that it cancels out the effect. Okay, that is the adaptive signal processing, where you learn all these techniques, LMS and LMS, so how it works, that always, all the time, you are changing the coefficient of your equalizer. So what is an equalizer? It is an FIR filter. It basically is an FIR filter. Let's say if it is 4 taps FIR filter, H0, H1, H2, H3. If it is 4 taps. Sometimes you need to have an FIR filter with 512 taps. Okay, in telephony usually, once we were working on voice over IP, there you need to have a 512 tap FIR filter, and you have to all the time keep changing all the 512 taps, because they are changing. This is the filter. Okay, so there will be 2 steps. One is you update the coefficients. And how do you update? You update because you send something known 2 ways. One is you send something known here, and what you receive is not what you send. So you know the error. So the error is used to derive the update equation. You say, I want to reduce this error because this is what I know I have sent. Okay, this is what I have received. So it is not what I have received. So you update the coefficients and try to receive what you sent. If you get to that, you say, now I am happy. Okay, this is really what I sent, so I am receiving that. And then you send unknown data. But you use the filter coefficients, same filter coefficients and unused data. And once it is unused data, you use, and again you send used data, the known data. So in every time you send known data and the information, because in known data there is no information. So you are wasting the bandwidth. So the known data is wasting the bandwidth. But especially in MIMO system, very complex. You have to send the known data. The known data, or the tones, they call it tones. This is called a Decision direct, or this is where the information is sent. Then there are several equalizers which does not require, though they do require preamble, but they still update the coefficient even once you are sending unknown data. Because how they know, either you are sending a sine or a cosine, or you are sending a sine with this phase or this phase or this phase or this phase. So they kind of know that really this is what you are sending. Okay? So very close to that. If they don't get this, they know that there is some error in the channel. So that error is driving the update equation of the coefficients. This is if you are doing the FIR, adaptive filters. But we'll focus more on IAR. Okay? IAR is that you say, okay, I want to design an IAR filter. And how to do that. So we'll start discussing it next time. Though this, the statistical signal processing does require a fair amount of background in stochastics, and I don't know if any one of you has taken stochastic. If not, it is fine. We'll try to at least give you a general background what is meant by stochastic, because the stochastic or randomness is important in statistical signal processing. You can always, the deterministic versus the adaptive. What is the difference? The difference is deterministic is against something which is known to you. Okay? I have given you this example several times. If you are designing a satellite receiver, you precisely know this is your band and everything which is not your band is out of band noise. So you want to throw that away. So you design deterministic filter. You precisely know that this is the spectrum which you want and rest you want to throw away. This is deterministic signal processing. The problem is that many a time the noise is random. You don't know. The channel is random. It is just changing all the time. And it is in-band noise. It is getting into your spectrum. So designing something like this will not help you because you don't know, first of all, noise does not exist in a separate spectrum. It is part of your signal. Okay? So you have to combat the noise. How you combat it? You try to find out the source where it is being generated. You cannot guess it. You cannot say, I know the noise will be like this. You cannot do that. But the noise, the good thing about noise is that it really has some statistical properties. For example, you say it's a zero mean noise. If you add noise samples together, you'll get zero. So these are something good about noise, that at least though you cannot just say this is noise, like you cannot predict noise, but you can know some higher order statistics of noise, that it will always add up to zero because it is noise. So you know some higher order statistic of noise, and those statistics are used to design these things. If you don't know those statistics are wrong, then you cannot really. So that will require us to do that. But the first part will be the modeling. The modeling will be, as I mentioned earlier, the modeling is where you will have a signal and you will try to model it. You'll try to generate all the samples of the signal through a mathematical model. Okay? So we'll do that part, and then we'll see if we have time. We'll come to the stochastic part. Okay?